Questions 21 through 25 on the 2021 Grade 7 Gauss Math Contest. A large number is written with 1 followed by many zeros. When 1 is subtracted from this number, the sum of the digits in the result is 252. How many zeros are in the original number? Let's explain this with a few examples. Let's say the number was 10. Then you subtracted a 1. Well, that obviously is 9. Sum of the digits, well, just 9. If the number was 100, you subtracted 1. That would create a 99. Sum of the digits here is 18. If it was 1,000, that original number, and you subtracted 1, the result would be 999. Sum of the digits is 27. You get the point. So what they've done is they've told you this part, the sum. They've said that eventually you're going to have a situation where the sum is 252. And they want you to figure out how many zeros are in that number. Okay, well, this was 9 times 1. This was 9 times 2. This was 9 times 3. What's 252? 252 is 9 times 28. So let's see. Over here, this is 1, we had 1 9. This is 2, we had 2 9s. This is 3, we had 3 9s. In a very similar way, this was 1, we had 1 0. This was 2, we had 2 zeros. This was 3, we had 3 zeros. So since this is 28, we would have 28 zeros. ... And that's pretty much all that they're getting at in this question. So number 21, the answer is B. In the diagram shown, each figure after figure 1 is formed by joining 2 rectangles to the bottom of the previous figure. Each individual rectangle has dimensions 10 by 5. If figure N has a perimeter of 710, the value of N is. We have the figure, and then we have the perimeter. So let's see what we get. ... Hopefully we're going to have to get some sort of a pattern here. And then perimeter I'll put over here. So the first 3 perimeters I can get just from these diagrams right here. The first perimeter, it looks to me like, let's use a different color, 10, 10, 20, 30, 40, 45, 55, 60. So the first perimeter, you can just count, is 60. Second perimeter, in a very similar way, you can do the counting. You don't need to hear me do the counting. You'll figure out that that perimeter is 70. Keeping in mind the dimensions are 10 by 5 for each of those blocks. The third figure, the perimeter, is 80 when you do the counting. So obviously there's a steady pattern here. It's going to increase by 10 each time. So in general, for any n, it would be 60 plus 10 multiplied by a certain factor, and that factor is just n minus 1. And you can verify that this formula is indeed the correct one by plugging in values of n equals 1, n equals 2, and n equals 3. It's not that difficult of a formula to come up with. Now we are told 710 is the value for some n. Okay? How do I figure out n? Use this formula. I'll do that over here. So I got 60 plus n minus 1 times 10, and that equals 710. So let's multiply this out. 10n minus 10, 710 minus 60 is 650. So 10n is equal to 660, and therefore n is equal to 66. And that's it. Number 22, the answer is C. To encode a message, James first replaces each letter within the message with its corresponding number, where A is 1, B is 2, ... Y is 25, Z is 26. Next, James multiplies each number by 3, then subtracts 5, and continues this process a total of n times. For example, when n is 2, the letter D is encoded to the number 16. If James encoded a 4-letter message to the 4 numbers 367, 205, 853, 1339, what is the value of n that he used? First, let's figure out what's happening here. Let's just say we use D, which is what they're using, so let's just use the same thing. D would have value of 4. according to this sort of pattern. A is 1, B is 2, C would be 3, D would be 4. When we run this 4 through the first process, you have to multiply by 3, then subtract 5. So we would take our 4, multiply by 3, and then subtract 5. And that is 12 minus 5, which is 7. Now, we're doing this twice because n is 2. N represents the number of times that you do this process. Okay, let's do it a second time. So you take that 7, you'd multiply by 3, and then you'd subtract 5. So this looks like 21 minus 5, which is 16. And that's what they are saying. So they gave you an example. I just kind of wrote out the example. Now they're saying that you are taking 4 letters, and then eventually those 4 letters convert to these numbers. They want you to figure out what is the value of n, meaning how many times did you have to go through this process? Okay, well, I don't know. So let's try to figure out how many times. And let's just concentrate on one letter. Let's just concentrate on that letter. Now, I have no idea what that letter is, so I'll just represent it with X. Not the letter X, just X as unknown. I don't want this to be confusing. I could use another symbol, but I think you guys understand. Okay, when n is 1, that means you only go through this process one time. So you take that number, you multiply by 3, and you subtract 5. Now, I want to see if n could be 1. Well, n equals 1 is not even one of the answer choices, but just for the sake of completeness. Can I get a 367? Well, that would mean that 3x minus 5 would be 367. Okay, solve for this. And when you do, you get x is equal to 124. Now, that's not possible because the largest value that you can get for any particular letter is 26. So, obviously, I can't get 124 as a letter. So, n obviously is not 1, and that's not a surprise. Now, let's try n equals 2. And that means you take this number, and you multiply by 3, and then you would subtract 5. And when you do this math, you get 9x minus 20. Okay, well, if 9x minus 20 can equal 367, this will work. Let's see. 9x minus 20 equal to 367. When you solve this, you get x equal to 43. Okay, again, that's not possible because the largest value is 26. Okay, so we can eliminate that. How about n equals 3? Same thing, you would take this, 9x minus 20, multiply by 3, subtract 5. When you figure that out, it's 27x minus 65. Okay, let's put that to the test. 27x minus 65, can that equal 367? When you solve this, you get x equal to 16. All right, that works. So you think, okay, well, that's the answer. Well, not quite yet, because we have to test out the other 4. All 4 have to work. So let's test out the other 4. So 27x minus 65, can it equal 205? When you solve for that, you get x equal to 10. Great. Let's try the 853. Let's see what happens. So we got 27x minus 65 is equal to 853. And therefore, that would mean x is equal to 34. Oh, that's a problem. X cannot be 34. The maximum value for a letter is 26. Okay, so it's not 3. Well, I'm confident that it's going to be the next one, which is x equal to 4, but I have to prove that it is correct. When you do this process again, you get 3 times 27x minus 65, and then don't forget the minus 5. So this now gives me 81x minus 200. Put this to the test now. 81x minus 200. First, I got to test it out with 367. When I do, I get x equals 7. Okay, great. Let's test it out now with the next one, which is 205. Like that. When you do that math, you get x equal to 5. Okay, that works. Let's do the other two up here. 81x minus 200 is equal to 853. When you do that math, you get x equal to 13. Okay, that's also valid. And then the final one, 81x minus 200 is equal to 1339. When you do that, you get x equal to 19. So it all works out. So the answer is indeed 4. If you went to 5, if you did this process again, my instinct is that you would start getting non-integers, like 3.3 or something like that, for values of x. And obviously, the numbers have to be integers. So number 23, the answer is C. How many different pairs of positive whole numbers have a greatest common factor of 4 and a lowest common multiple of 4620? I want to do a little bit of a primer before I get into this question. GCD, greatest common divisor. They're calling it greatest common factor. I'm used to using GCD. Same thing. And then LCM, lowest common multiple, or least common multiple. Well, for GCD, I want you to always think minimum. And I'll explain what I mean. And for LCM, I want you to always think maximum. It's kind of counterintuitive. For the greatest, you got to think minimum. For the least, you got to think maximum. But let me explain what I mean with an example. So let's say I said to you, I've got two numbers in mind. I want you to find the GCD. And those two numbers are 2 to the power of 1, 3 to the power of 2, 5 to the power of 3. And the other number is 2 to the power of 1 times 5 to the power of 2 times 7 to the power of 4. You can choose any two numbers. I just chose these. The first step, which I've already done for you, is you have to break it up into its prime factors. Because if I gave you numbers like, 1, 2, 8, 6, 4, you have to first break this up into its prime factors. What is it? 2 to the power of what? 3 to the power of what? Like that. Obviously, that's a necessary step. So how do you figure out the GCD? Think min. You look at each prime factor and you choose the minimum that it occurs. So for 2, what's the minimum that it occurs in both? Here it occurs only once. Here it occurs only once. The minimum is once. So that's part of the GCD. The next prime factor is a 3. It occurs here twice, but it occurs here 0 times. So the minimum is 0. So that's what goes into the GCD. Next prime factor is a 5. It occurs 3 times here, but it occurs only twice here. So the minimum is twice, so you put 5 to the power of 2 there. The next prime factor is 7. It occurs 4 times here, but it occurs 0 times there, so the minimum is 0. So the GCD is just 2 times 5 squared, 25, which is 50. Okay, so now LCM. LCM is think max. Let's just use the same numbers. No reason to choose anything different. 2 to the power of 1, 3 to the power of 2, 5 to the power of 3, and then the next number is 2 to the power of 1, 5 squared, and 7 to the power of 4. Okay, LCM think max. First prime factor is 2, right? It appears once here, once here. The maximum it appears is once. So put 1. 3 is the next prime factor. It appears twice here, but it appears 0 times there. The max is 2, so there goes the 2. The next prime factor is 5. It appears 3 times here, twice here. The max is 3, so you put 3 here. And the 7, it appears 4 times here, 0 times here. The max is 4, so there you go. So this is obviously some big long number. And this, when you figure out what that number is, it's the LCM. So that's how you figure out GCD and LCM. All right, so now that you're an expert, let's start the question. So we are asked to find different pairs, so only two numbers, that have a GCD of 4 and an LCM of 460. So I'll just call the numbers A and B. I have no idea what they are, right? So that means I've got to find a GCD of A and B to be 4, which is 2 squared. I always want to put it in prime factor. And then I've got to find LCM of A and B. I've got to ensure that it's 4620. But 4620 is 2 to the power of 2 times 3 to the power of 1 times 5 times 7 times 11. Okay, so let's figure this out. Remember, GCD was think min, correct? So that means my A has to have a 2 to the power 2 in it. That's the only way that you're going to get a 2 to the power 2 in the GCD. And same thing with the B. The B has to have a 2 to the power 2 because we got to take the minimum. At least 2 to the power 2 has to be in both. That's the only way you're going to get a GCD that has 2 to the power 2. But the rest of A and B can be anything, and they cannot have anything in common. So for example, if we had a 7 here, there can be no 7 there, because if there was a 7 in here also, then that would become part of the GCD. So the rest it doesn't really matter. All I know for sure is that A and B have to have 2 to the power 2 as part of the numbers. Let's turn our attention to A and B talking about this. Now we have A equals 2 to the power 2 for sure, and B equals 2 to the power 2 for sure. But now we are thinking max. And we have to get all this other stuff. This, 3, 5, and 7. Well, the only way that's possible is if you have a 3, a 5, a 7, or 11 in either A or B. So one example would be you have a 3 and 5 up here, and you have a 7 and 11 down here. So A is equal to, say, 2 to the power 2 times 3 times 5. B is equal to 2 to the power 2 times 7 times 11. When you figure out the LCM, it would be this. But that's not the only way of doing it. There's several combinations. So here are the combinations. The first is you could have all 4 of these prime factors in A and 0 in B. So for example, you would have A is equal to 2 to the power 2 times 3 times 5 times 7 times 11, like that. All 4 are in A, and B has none of them. B is just 2 to the power 2. And therefore, that would be one scenario. So this gives me one pair. I'll just put that in brackets. The other way is to have a 3 in 1 scenario, where A has 3 of these 4 numbers, and B has the other 1 of the 4 numbers. So that is going to be 2 to the power 2, 2 to the power 2, but any 3 of these 4. So that means from 4 you're choosing 3, right? So that's what? 4 choose 3 is 4. So there's 4 ways of doing that. So I put the 4 in bracket. And if you're curious, you really want me to write it out, I'll write it out. It's not a problem. You can have, for example, a 3 here and a 5, 7, and 11 there. Or you could have the 5 up there and the 3, 7, and 11. Or you could have a 7 and a 3, 5, and 11. And you could have an 11 in the A and a 3, 5, and a 7 in the B. So 1, 2, 3, 4. That's how I got 4. Okay, hopefully that is making sense to you. Now let's move on. We did the 4 and 0. We did the 3 and 1. How about the 2 and 2? A 2 and 2 scenario. That's also valid. So 2 and 2. So that means 2 of these numbers go in A and 2 of them go in B. So for example, we have 2 to the power 2 and 2 to the power 2. That doesn't change. But for example, you have 2 of those numbers in A and 2 of those numbers in B. So from 4 numbers, you're choosing 2. And 4 choose 2 is 6. So there's going to be 6 ways of doing that. And I'll just write them all out. 3, 5, and 7, 11. Like, for example, you put 3 and 5 up here and 7 and 11 here. Like that. That's one way. 3, 7, 5, and 11. 3, 11, 5, and 7. 5 and 7, 3 and 11. 5 and 11, 3 and 7, and 7 and 11, 3 and 5. But some of these are doubles. 3, 5, 7, and 11, you notice this is the same as that. 5, 11, 3 and 7, that is the same as that. And 3, 11, 5, 7, this is the same as that. So there's only actually 3 unique pairs. Because remember, they want unique pairs. How many different pairs? They don't want the same pairs. Different. Okay, so I did 2 and 2. Now let's do the next one, which is 4, 0, 3, 1, 2, 2. The next one would be 1, 3. Well, 1, 3 would give you the exact same as this, and it would not give you anything new. It would not give you any new unique pairs. So I'll just say same. Okay? And then the last one is going to be 0, 4, where 0, 4 is going to be the same as this scenario. It's going to give me the same one pair. So let's see, how many unique pairs did I get? I got 1 here, I got 4 there, and I got another 3 here. So that is 8 unique pairs. And therefore, the answer to number 24 is D. Jonas has 1728 copies of a 1 by 1 by 1 cube with the net shown, where C is a positive integer and C is less than 100. Using these 1728 cubes, Jonas builds a large 12 by 12 by 12 cube in such a way that the sum of the numbers on the exterior faces is as large as possible. For some values of C, the sum of the numbers on the exterior faces is between 80,000 and 85,000. The number of such values of C is. Well, let's make a cube, and let's talk about this now. So this cube is going to serve as our diagram. Now, I'm going to draw a smaller cube, or not cube, but a smaller square inside of it. And I will illustrate a few things here. Now, when we are drawing these cubes, we have to understand that this is going to create the full shape. And there's a few types. The first is the corners, like that. That is one such shape. The second type are what I'm going to call sides, the ones that sort of come on the sides like that. That is a good example. And the third type of shape is just in the interior. We'll just call it in the middle. There's a lot of those. There's going to be a lot of those guys. So that is basically the 3 types. So we have either a middle, or we have a side, or we have a corner. And it won't take that much time to figure out each. So let's go through these. Each face of these cubes is a 12 by 12 face. The whole cube is 12 by 12 by 12, but each face is 12 by 12. So let's just write that. Each face is 12 by 12, which is 144. So there's going to be 144 of those small, squares on each face. But each face is broken up into middle, side, and corner, right? How many are in the middle, how many are on the side, and how many on the corner? Well, the middle, I think, is the easiest to figure out. We have 1 here and 1 here, so that makes this 10. Similarly, that makes this 10. So the middle is just a 10 by 10 square. So the middle is 10 by 10, which is 100. So there's 100 of those, 144, in the middle. Okay? Now the corner, well, the corners are easy, right? There's only 4 corners. There you go. You got 1 here, 1 there, 1 there, and 1 there. So 4 corners on each face. So just put a 4 there. And then so far I had, of the 144, 100 allotted here, 4 allotted here. That leaves 40. I don't even need to count. I can just subtract it from 144. So 100 in the middle, 40 on the sides, and 4 in the corner. Okay. So now we're ready for the next step, which is to figure out the total. The total, of course, will be very similar. The only thing we have to do is multiply by 6 because there's 6 faces. We did this for each face, but there's 6 faces to a cube. So middle, it would be 6 times 100. And that's 600, of course. And then we have to get the maximum sum. The sum on the exterior, the numbers have to be as large as possible. Well, the ones in the middle, they only take up one of these, correct? Only one of those will show on the exterior. The other ones will be buried inside the cube. And of these, the maximum is 100. Why? Because C is less than 100. So each of those will have 100 if I choose 100 as the face being shown on the exterior. So that will give me 6 times 100 times 100, which is 60,000. So 60,000 will come from those guys. That's the maximum I can make it, the ones in the middle. Same philosophy for the side. I've got to multiply the total by 6 because there's 6 faces, 40. But here's the thing. On the side, 2. You notice? 1 and 2. 2 faces show from this. Okay. From one of those, first let's just figure out what this is. This is 240, right? Okay. We got to break that up into 2. Half and half, right? Because each of those sides will have 2 faces. For one of them, I will choose the 100. So then I multiply that by 100, and I get 12,000. But then for the other one, I can't choose 100 again. I've got to choose one of these C's. So I'll multiply that by C, and I get 120C. So that's about all I can do there. That's the maximum I can make it. Now the corners. First, we got to multiply it by 6. Gives me 24. Correct? But the corners, there's 3 faces showing. 1, 2, 3. Okay? So the 24, I got to break it up into 8, 8, and 8. Right? Because I've got to look at it from the perspective of those 24 have to be divided into 3 sections. The first section, I will put 100 as the max. So I can multiply that by 100. That's 800. The next one, if 100 is allotted, then the other ones have to be C's. So this one I have to multiply by C, and this one I got to multiply by C. So that's 8C, and that's 8C. And that's it. That's pretty much the total. So now let's add it all up. What is the total? It's this, plus this, plus this, plus this, plus this, plus this. Okay? So that is, let's see here, in terms of numbers, 72,000 and then 800, right? So 72,800. And in terms of the C's, it looks like 120 and 8 and 8. So that's 120 plus 16. So 136C. Yeah. And they're saying that's between 80,000 and 85,000. Okay? So it's between 85,000 and 80,000. Okay, I think that's a fairly straightforward inequality to solve. So here we go. First thing is bring the 72,800 to one side. And if I subtract it from both sides, I'll get 200 on that side and 7,200 on one side. And then divide through by 136. And that brings me to just C in the middle. This side will be 89.7 approximately. And on this side will be 52.9 approximately. Well, C is an integer, right? Yeah, C is a positive integer. So because C is a positive integer, I can't use these decimals, so I've got to use the integers. If C is less than 89.7, then that means it must be less than or equal to 89, because that's the first integer below 89.7. Similarly, if it's greater than 52.9, it's got to be less than or equal to 53. So there you go. C is any integer between 53 and 89 inclusive. So that means the number of values for C are 89 minus 52, right? You're counting all the integers from 53 to 89 inclusive, and 89 minus 52 is 37. And there you go. 37 is the answer to number 25, and that would be C.